Hello everybody. So here's a question that just came in from assignment 3.2, and like a lot of word problems, it might be a challenge to read this and figure out what to do with the information. All right, set it up and then solve it. Okay, that's, I think, the challenge with any kind of problem like this is understanding what we're looking at, and maybe drawing a picture or doing whatever you have to do to sort out the information. So I want to go through all that. I'll start by reading it and tell you what my thoughts are about what this seems to say and show you how I would think about it, set it up, and solve it from there. So it says we're designing a poster. It has to contain 12 square inches of printing, has to have a 1-inch margin at the top and bottom. Okay, so those are rows of the poster with no printing on them at all, and 3-inch margins on the side. So again, 3-inch strips on each side with no printing. What overall dimensions will minimize the amount of paper used? So the truth is, there's a lot of ways you could put this together so that it has this much printing on it with these margins. All right, but there's one way that will get the minimum amount of paper used with the printing and the margins the way that it's described. Okay, so here's the way I would think about it. So imagine, like, I'm reading the problem and I'm kind of thinking about it like this. Here's what's going through my mind. This is my imagination at work. Okay, it's rectangular. All right, it's got a width and it's got a length to it. And then there are these margins that I have there in red. It said a 1-inch margin at the top, a 1-inch margin at the bottom, 3-inch margins on each side. And then in blue there, that's the part of it that's got the printing on it. All right. So that's, when I read it, what I think that I'm looking at. Okay. All right. Now the setup from there would go something like this. In a problem that's an optimization problem, and this is an optimization problem, meaning that I want to minimize or maximize something, then I will have whatever I'm trying to minimize or maximize, and I'll have some kind of constraint. Okay, like if it weren't for the constraint, the minimum would be 0, but I have to have 12 square inches of printing on it. So here's the setup. The constraint is that I have to have 12 square inches of printing on it. Okay, now as I look over here and I say, well, here's my poster and it's got an overall width and it's got overall length to it, then actually the part of it that has printing on it is this number W, take away 3 and take away 3 again. Okay, so this blue part in here has an actual width of W minus 6, right? Because we got an outside width of W. If I got to take away 3 this way, okay, so that's W take away 3, and I got to take away a 3 again. That's why it's W take away 6. Okay, all right, and then this other side right here, the length for the part of it that has actual printing on it is the overall length L, take away 1 on the top and take away another 1 on the bottom. So that'd be L minus 2. Okay, so we got W minus 6 here, L minus 2 here. So the part that has printing on it has an actual width of W, the overall width, minus 6, and an actual length of L, the overall length of the poster, minus 2, to account for the margins. Okay, now that's got to be 12. Okay, so here's our constraint right there. Okay, and I want to minimize the size of the poster, the actual size of the poster as it is. Okay, now that would be its area, which is its length times its width. Okay, all right, so I started with this picture in order to help you visualize what we would read. Okay, and then from that I had to do a little bit of math to figure out what the constraint is and what I'm trying to minimize. Okay, now here's how we solve this kind of problem from here. Ultimately, if I want to minimize something, whatever that is, an area, a cost, a volume, it will amount to me finding the derivative of that and solving it for 0. Okay, so the fact that it says to minimize is going to take me here, but in order to get to that point, I have to reduce this equation, the area equation. I want to minimize the area is length times width. I got to reduce that to just one variable. So we use the constraint to do that. Okay, so I'll solve this constraint for either the width or the length, and then I'll sub that into the area equation, and that will reduce it to one variable. Okay, so the way that I do that is I'll take this constraint, I can solve it for W or L, it doesn't really matter. I'll divide both sides by W minus 6. That'll get me L minus 2 equals 12 over W minus 6. My aim is to solve that for L, so I'll now add 2 to both sides. I'll get L is 12 over W minus 6 plus 2. And then, as I mentioned, I'm going to substitute that in here to reduce it to one variable. So imagine if I took, in place of that L, I took 12 over W minus 6 plus 2 and I put it in there. Then that would give you this, 12 over W minus 6 plus 2 times W. And then from there, I'll distribute the W. I'll get 12W, all right, over W minus 6 if I multiply like that, plus 2W. Okay, so now that reduces the thing I'm trying to minimize to one variable, all right? It says area equals 12W over W minus 6 plus 2W. Ultimately though, like I said, I want to solve A prime equals 0. So now my second step, I'll say calculate A prime. If I want to find the derivative of this, I'll have to use the quotient rule, that's what you're looking at here. And then plus, I carry the plus down. What's the derivative of 2W? It's just 2. Okay. If this is simplified, much of what I have there cancels, and I get negative 72 over W minus 6 squared plus 2. Okay. So like right now, at least I'm not explaining the quotient rule. You know, if that is something that we needed to review, you could ask about it. We could go over it. But here's the derivative with the quotient rule. That's what it simplifies to. Okay. So here's my A prime. That's my derivative. As I mentioned when I started this, ultimately I said I'm gonna to find the minimum. I'm gonna find the derivative of this and solve it for 0. So I now have the derivative. I set it equal to 0. I subtract 2 from both sides. With some cross multiplying, I'll reduce this to W minus 6 squared is 36. Simplifying a little further, I'll get W squared minus 12W is 0. Solve this by factoring. Factor out the W, I'll get either W is 0 or W minus 12 is 0, which gives me W is 0 or 12. Okay, 0 can't be the answer. It wouldn't be meaningful to have a width of 0 inches on this poster, so it's got to be 12. All right. Okay, so when I solve it, I find that the width needs to be 12 inches. Okay, so this overall width right there needs to be a foot, 12 inches. What's the length though? Okay, well I guess with any word problem we should try to clarify what's it asking for. The dimensions of the poster that minimize the amount of paper used. That means minimizing the area. Well, so by dimensions they mean what's the length and what's the width. Okay, all right. So I got the width. It should be 12. I'll have to look over here in my equations if there's some way to find the length if you know the width. So let's look at our equations. Does any of these seem to, like if you knew what W was, tell you what L was? This one right here. Okay, so we'll use that one. We'll get L is 12 over W minus 6 plus 2. So W is supposed to be 12. Imagine if you put a 12 right there. Okay, 12 minus 6 is 2. 12 divided by 2 is 6. Okay, and then 6 plus 2 is, I'm sorry, W minus 12 minus 6 is 6. Okay, 12 divided by 6 is 2, and 2 plus 2 is 4. Okay, so we'll get 4 out of that. Okay, so putting it in like this gives me 4, and that's how I'm saying what that is. So here's my answer. The dimensions, the poster should be 12 by 4. All right, that will minimize the amount of paper used and still give you the, you know, if you needed 12 square inches of printing on it, it's still going to work out. Okay, let's do this. Show you how to put the answer in. See how it says give the dimensions of the poster that minimize the amount of paper used. It says use a comma to separate answers. So I just put both of those numbers in. I put 4, 12, and understands that as giving length and width. Okay. All right, so that's how we do this one. I would say though that these steps here in red are typical for optimization problems. Reduce what you want to minimize or maximize to one variable using the constraint. Find the derivative, solve it for 0. That part's not too unique from all the other problems, but reading this one may have been the biggest challenge. So I guess when we're doing this kind of thing, I have to read it carefully, and at least for me, like, I really need some kind of picture to think about, either in my mind or actually to look at it on paper.